So, welcome back. So, today we are going to discuss about to start with some symmetric of the function, that means on the positive and the negative axis there is some symmetry. So, which we are quickly we can say that a function is said to be even function if f of minus of x is equal to f of x. So, now if we know the value of the function on 0 to infinity, then obviously we know immediately that it will look like exactly the similar kind of thing from minus infinity to 0. So, what are the example of this function? So, this is f of x equal to mod x, as we have seen that this is what it is going to be, f of x equal to mod x, and f of x equal to x square, this whatever f of minus of x is going to be f of x, and f of x equal to cos x. So, now this cos is, and then on this side this is just the symmetry like this. So, however, if you look at f of x equal to x plus 1 square, this is not an even function. Even is f of minus of x is equal to f of x. That means, around the y axis it is symmetric, but f of x plus 1 whole square, this is not an even function, because if you take x equal to minus of 1, then f of minus of 1 is going to be 0. Now, if you take f of 1, then this is 1 plus 1 square, that is 4, which is not equal to 0. So, therefore, f is not an even function. Similarly, we can define a function to be odd if f of minus of x is equal to minus of f of x for all x. For example, this what we have seen is f of x equal to x, f of x equal to x cube, and f of x is equal to sin x. Sin x is like this. Now, here on the negative sign, this will be look like this. So, f of x equal to sin x is an odd function, f of x equal to cos x is an even function. Now, if we look at f of x equal to x plus x square, now it is neither even nor odd. So, there can be functions which are either even function or odd function, or neither even nor odd. So, now another important thing to know about this function, which will be very useful, is the increasing and decreasing functions. So, what is an increasing function? A function is called increasing on an interval I. You see, this is where a function may be defined on the entire domain. So, here we are only if I may be a subset of your domain D. So, f is increasing on that interval I if f of x 1 is less than f of x 2, if x 1 is less than x 2 in I. Not necessarily that it has to satisfy this on the entire domain. So, what we will see in that interval I, f is an increasing function. A function is said to be a decreasing function on an interval I. This is very important, on an interval I. So, if f of x 1 is greater than f of x 2 whenever x 1 is less than x 2 in I. So, for example, this is a function, you can see that this is increasing up to 1, and then after that this is a decreasing function. So, similarly, you can have this sort of function. So, you can see that in this sort of function. So, in this interval, this function is an increasing function, but in this interval this is a decreasing function. Now, if you take this interval, let us say about this interval, then I cannot say that in this interval it is neither increasing nor decreasing, because here is a point and x 1 is greater than. So, this is the function suppose this is x 1, this is x 2, then f of x 2 is greater than f of x 1, but now here in this interval f of this, let us say this is x 3, then f of x 3 is less than f of x 1. So, we have to check that in which interval f is increasing or decreasing. So, the above function is increasing, this is increasing in up to 1 and then decreasing if x is greater than 1. Now, what we have seen is that we can because we have a real number, then we can define the integer power of that real number very easily, because we have the multiplication, and if it is a negative, then you define it as the denominator and take this. Now, for alpha greater than 0, we can define alpha to the power p if p is a rational number, because we know that alpha to the power 1 by q, suppose you have alpha to the power p by q you want to define. We know that q is an integer. So, alpha to the power 1 by q exists, because qth root exists. So, now I take to the power whole to the power p, this is nothing but alpha to the power p by q. So, now if alpha is greater than 0, then we can always define alpha to the power p for p belongs to q. Now, if alpha is greater than 1 and x is in R, now let us define f of x to be alpha to the power x, x now is in R. So, what we want to get is that we want to get, now this can we define that alpha to the power x, that is what we are asking for. Now, f of x equal to, this is how we are going to define, you take alpha to the power R, this is defined because alpha is greater than 1, that means alpha is greater than 0, and R is a rational. So, alpha to the power R is defined. Now, you take the set alpha to the power R for all R less or equal to x. Now, this is definitely going to be a bounded above set, therefore, the least upper bound will exist and I will call that to be alpha to the power x. So, for alpha greater than 1, you see this is slightly complicated in defining, this is what it is talking about, the existence of real power for a positive real number. So, what we are doing is that we are saying that if we have a positive real number, then we can define the rational power, that is what we had defined, and now for the then we take the supremum of certain set least upper bound to define alpha to the power x. Now, for if I have 0 is less than alpha less or equal to 1, then obviously 1 by alpha is greater than 1. Therefore, I can define 1 by alpha to the power minus of x, because x is a real number, then minus x is also a real number. So, we can define now what we can say is that actually if alpha is positive, then we can define alpha to the power x. Now, let us take 0 and x is in R and alpha beta it is a positive real number, alpha and beta they are two real numbers. Then what we have seen is that here the x to the power alpha is defined because x is greater than 0 and alpha is any real number. X to the power beta is defined. Now, so definitely these two are real number. So, we can define x to the power alpha into x to the power beta, that what we know is that it is a real number, because real number is a field. Now, what is that? That with this definition, one patiently if one writes down this definition is x to the power alpha and x to the power beta, then what we can see so is that x to the power alpha into x to the power beta, this is equal to x to the power alpha plus beta. So, you take this alpha plus beta, then x is a positive real number, alpha plus beta is a real number, you define x to the power alpha plus beta. Similarly, x to the power alpha you take, this is a real number, x is a positive, alpha is any real number. Now, you take the whole to the power beta. So, this is definitely going to be what one need to show is that this is going to be greater than 0, and so this is going to be x to the power alpha into beta. This is the law of indices what we have done for the rationals also. Similarly, if I take x y to the power alpha, this is going to be x to the power alpha into y to the power alpha. For obviously, any power if I want to define, then we need to assume that x and y both are positive real number. And if 0 is less than x less than y, then the power is going to respect the inequality x to the power alpha is less than y to the power alpha, provided alpha is not equal to 0. I mean alpha is positive, this is what we are going to say. Okay. Now, if x is greater than 1 and alpha is greater than beta, then x to the power alpha is greater than x to the power beta. Okay, so, now 2 to the power x, if I want to draw the graph, this is going to be, you can see that it will go like this. So, this will be always a non-negative number, 2 to the power x will be always greater than 0 in fact, and then this grows exponentially. So, this is what is the graph of 2 to the power x. Now, similarly, what we can define once we have this function exponential function, we can define the logarithm. So, which in a sense we will see later that it is an inverse of this function. We will define what inverse is at its later stage. Now, if 1 is not equal to a, which is and positive, we call x as the logarithm of y greater than 0 with respect to the base a. If we define log y, y is positive, a is not equal to 0 and a positive real number, and x is this any real number, then if a to the power x, as you can see that a is positive, x is a real number, a to the power x is a well defined object. Now, this means that a to the power x is equal to y. So, this we call that the log y to the base a is x if a to the power x is equal to y. Now, what one can show again with the logarithm, log for any base a, x y is equal to log x plus log y, log x by y, y not equal to 0 positive, then this is log x minus log y, and log y to the power x, y is positive. So, I can define y to the power x, which is equal to x log y, and this nomenclature is that we will write log x to the base e as the ln x. Okay, this is what the graph is. So, this is your 0 and then this is 1, log 1 is 0. So, this is how this is going to look like your logarithm graph. Okay. So, now till now we have discussed various functions and which we cubed ourselves with trigonometric functions, and we have equipped ourselves with the exponential function, logarithm function. Then similarly, now from the algebra function we can define all these functions, the polynomial a n x to the power n plus a n minus 1 x to the power n minus 1 plus dot 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 plus a 1 of x plus a 0, because addition of the two function is a function and multiplication by the scalar is a function. So, polynomial. Now, also we have the rational function p x divided by q x, where both p and q are polynomials, and then trigonometric function, and then exponential functions and logarithmic function. Now, what we are going to discuss about is a very important concept of the function, that means which is comes in the calculus with the limiting process. So, well, now for example, you can think of this. Suppose I am traveling from a distance from, I want to travel from A to B. Now, in first 1 hour I travel half the distance. Then in the next 1 hour I travel the half of the remaining distance. Then next 1 hour I will travel half of the remaining distance. I will go on like this. You see, this process is not a finite process. However close we go, there will be some distance will be left. So, in the next hour I am going to travel half of that distance. So, that is let us see that what is the need of the limit what we are. Now, also geometrically we know that how important is to find a tangent to a curve. So, now let us see that I have a, let us see we have a parabola which is defined to be y is equal to x square by 4. Now, we are interested in finding the tangent at the point 1, and then this is going to correspond to 1 by 4. So, how can we find the tangent? Now, tangent is a straight line. So, from the coordinate geometry we know that, I mean, if we can draw write down the equation of the tangent if we know the slope. So, now in order to know the slope, the right kind of thing is to, if we know 2 points on the tangent, then we can calculate the slope of the tangent. Our problem is that we had been given a parabola. Now, we want to find a tangent at a point. So, we know we have information only about one point of the tangent, because this tangent is going to touch the parabola only at one point, and rest of the things, all these points in the tangents, they are not in the parabola. So, we do not have any information about any other point of that tangent. So, now how we are going to address this problem? So, let us try to do this. Let us get the parabola for us, and here is the point P in which we would like to find the tangent passing through P. Now, we do not know any other point. So, what we do instead is that we take any point Q, let us say this is Q, on the parabola. Then I join the line PQ, line passing through PQ. Now, I have 2 points, I have information about P and as well as Q, because I know whatever the value of the Q is, and it is a point in the parabola. If this is 1 1 4 and if this is 2, then this is going to be 1. So, I know P and Q with a specific x coordinate. So, I can find out the tangent, I can find out the slope, then I will draw the line passes through P and Q. So, now what I do next is that I shift my point Q to closer to P, and I join this. So, now I will continue with this process, then again I will have Q here, then I join the line. So, what you can observe is that, and I keep on calculating the slope of all these lines. So, what we will see is that as we are coming closer and closer to P, on the parabola, then the slope is coming closer and closer to half. So, now what does, and that is how we are going to get the slope. So, this is a limiting process. So, informally we write down limit x goes to a f of x is equal to a number L if the value of f of x, the value of, in our earlier problem, this is the slope, the value of f of x is as close to L as we like. By taking x sufficiently close to a, but not equal to a. So, which means if you look at, I can come to q here, then this is q here, and from both the side I can come, I can take my q to be this, and I will go like this, and this is what is approaching. So, what it says is that f of x is close to L, as close as we like, whenever x is very close to a, not equal to a. So, what does this statement means? So, first let us try to understand as close to L as we like. What is the meaning of as we like? That means, the difference between f of x and L has to be very small. Whatever the small we want to, we can make it that small. Small we want to make means, if I take any, so now if the distance, if I take the mod of this, then this is going to be a non-negative number. So, now this is going to be, as I want them to be as small, as close, f of x to be as close to L as I want. That means, f of x minus of L to be very small, whatever the small number you give me, let us call that to be epsilon. Let us give me a epsilon. I can find x such that f of x minus of L is less than epsilon. Now, that means, f of x is very close to L, as close as I want. Now, where the x are, the x also has to be close to the A, this point A. So, when this is going to, now we also need to consider what is the meaning of x close to A. X close to A means what? Let us consider the function. Let us try to understand it a little more. Now, consider the function f of x equal to sin pi by x. Now, this is function is defined for any x not equal to 0. So, now we want to check what happens when limit x goes to 0. So, if you look at, if I take x 1 by 10 to the power n, for large n, the 1 by 10 to the power n is going to be a very small number. So, if I take x equal to 1 by 10 to the power n, then sin pi by 1 by 10 to the power n is sin pi into 10 to the power n, which is going to be 0. Now, if you take n x to be 2 by 10 to the power n plus 1, this also can be very close to, if I take large n, then this x can be very close to 0, and in that case f of x is going to be 1. So, now how this is in one way, by taking some close point I am saying that this is going to 0, and in another taking some close point I am telling that this is going to 1. So, what is then the meaning of this x close to A? So, this suggests that we need to consider all the x close to A, but not equal to A, right. We can make f of x as close to L as we want when x is sufficiently close to A, and that has to be for all x which are close to A, but how close they are, that need to be determined. So, formally we say that limit f of x x goes to a is equal to L if for every epsilon, epsilon is our own thing, you can make it very small or this is our own property, epsilon is given to us. Now, for every epsilon, if somebody gives gives us an epsilon, then we can, there exists a delta, there exists a positive number such that f of x minus of L is less than that number which is given to an epsilon whenever this x minus of a, suppose here is a and this is a plus delta and this is going to be a minus of delta. Now, it says that whenever this x is lying anywhere in this except a, then f of x minus of L is less than epsilon. So, any epsilon, whatever epsilon somebody gives us, then we can produce a delta such that in this interval f of x is close to L, then we say that this is the limit of f of x, x goes to a is equal to L. So, that in other words, for any given epsilon, any epsilon, I am repeating it again and again. So, in any positive epsilon is given to us, then we must find a delta, and this finding a delta is going to depend on epsilon as well as the x. So, now if x belongs to a minus delta and a plus delta, but not a in this interval, then f of x must belongs to L minus epsilon to L plus epsilon. That means, f of x minus of L mod is less than, this is nothing but the same statement. So, which means the epsilon is given to us and our job is to find a delta. If we can find a delta such that f of x minus L is less than epsilon what is given to us, then we write that limit f of x, x goes to a is equal to L. So, we will do more concrete example in the next lecture to understand this concept well. So, let us stop here today. Thank you for your attention.